All right, this is Mr. Jern again, and today I'm going to show you how to deal with a problem that involves forces and an inclined plane. So we have here a 200 kilogram block that's sitting on an inclined plane whose angle of inclination is 15 degrees. And we have to find three things: the parallel and perpendicular components of the force due to gravity. We have to find the normal force, and then the force of friction that keeps the block from sliding. And then I'm going to talk about the coefficient of friction at the end. So let's always start by drawing the situation. Okay, so I'm going to just take a, just kind of sketch this in, a roughly 15 degree angle, and I'm going to put a block on it at that angle. Okay, it's not quite 15, but it's going to serve our purposes here. When we draw the forces, a lot of times we've been drawing forces from the edge of the block, and that's perfectly fine. It's totally acceptable. What I'm going to do here, though, is put a dot at the center of mass, and then I'm going to draw my forces from there. It just makes visualizing things and dealing with how they interact at the angles a little bit easier to manage. I'm going to start with my FG going straight down, my force of gravity going straight down. Okay, and if your lines are much more sloppier than mine, you might want to look to using a straight edge, but it's going to serve our purposes for now. Okay, now the next thing is, this is an inclined plane, it's going to keep going. It says it's just sitting there, right? The thing is, gravity is pulling on this thing. It's pulling it down, but it is pulling the block into the ramp and holding it onto it. And it's also trying to pull it down the ramp. So the force of gravity is trying to pull it down the ramp. It's also holding it into the surface of the ramp. So that means that we have a force of friction that must be holding the block there. And that force of friction will be pulling it or holding it, we'll say pulling it up the ramp in that direction. So I'm going to put an F, force of friction, and because it's static friction, I'm going to sneak a little S in there to remind me that it's static friction. Normal force is a little odd, or at least only because we're used to drawing normal force being in the opposite direction of gravity, because most things are sitting on a flat surface. This is not a flat surface, it's at an angle. And if you remember the definition of normal is something that's perpendicular to the surface. So our normal force in this case is going to be perpendicular to the surface, pointing away from it like that. Okay, so I'm going to put Fn for normal. Now, those are just sort of sketches. They're not really well represented to scale at this point. What's going to help with that is drawing the components of the force of gravity. I'll show you. And I'm going to do this I'm going to sort of take this block out of the environment and just draw a dot representing the center of mass. And I'm going to draw my forces from there. So gravity definitely pulls straight down. And so there's no question about that. But here's the thing. We are used to, we've done this before where we separate out a vector into its components. Usually it's been X and Y because everything has been, again, not at an angle. It's just been on a flat surface or something. But because we've tilted our entire world 15 degrees, we're going to sort of forego the X and Y, and we're going to talk in terms of parallel to the surface and perpendicular to the surface. So I'm going to resolve this vector. I'm going to break up this vector into components that are parallel and perpendicular to the surface of the ramp. So this is what I mean by that. I'm going to draw a dotted line perpendicular to the ramp. That is the force of gravity that is pulling the block into the ramp and holding it there. And so I'm going to label that FG perpendicular. That's the symbol for perpendicular. At a 90 degree angle to that, and it's kind of close, I suppose, is the force of gravity that's parallel to the ramp. That's the amount of force that's actually pulling the block down the ramp. Okay, so this gives us a sort of a better visual about the relative sizes of all the force vectors that are involved. The force of gravity that's pulling it down the ramp, this FG parallel, is being balanced out and canceled out by the frictional force that we drew earlier. So I'm going to try to draw this arrow about the same size as that arrow to represent my force of friction, static friction. And then, because gravity is pulling it into the block into the ramp with this Fg perpendicular, the normal force is, because nothing is accelerating in any direction, going to balance that out. And so I'm going to try to do my best, and I should be using a ruler here, and it's okay that I don't though, because I'm just showing you. But this vector here and that component of the vector are going to be the same because, well, the normal force, I'll use a capital letter here, will be completely inconsistent, but that's normal force, and that will equal that. So we've kind of sketched out our drawing, and they're fair, close enough to scale. So now letter A says we need to find the parallel and perpendicular components of the force due to gravity. So we actually need to find the numbers. So let's do that. So letter A will be to find the parallel and perpendicular force of gravity. I'm just going to draw that triangle all by itself. All right. So I'm going to kind of just start with the dot again, and I'm going to draw my force of gravity straight down. Okay, I'll just label that Fg, and then I will put my parallel. Sorry, this is perpendicular to the ramp. It's a little more than 15 degrees, but that's okay. And my perpendicular, I got that backwards. This is my. If I write it down, I won't get it wrong. Force of gravity parallel, and this is my force of gravity perpendicular. All right. Now the way it works. And we get into, I don't want to get into all that, but basically the way it works is this angle right there is going to be equal to theta. Okay, that's going to be the original 15 degrees that we were given. Okay, it just has to do with how much it was tilted and the insides of the triangles and how the complementary angles and all that. Okay, and if you have any questions about that, let me know. Or there's other resources out there that will explain that better. Okay, so that gives us a theta to work with now. So that means we're going to use our trig functions. We want to find perpendicular and parallel components. That's not going to be too much of a problem at all. We just need to remember, okay, sine of theta is opposite over hypotenuse. So katoa. So get it. That means that the opposite side for us, let me just label it over here, adjacent. The opposite side is going to be our FG parallel, and our hypotenuse is going to be FG. Okay. We want to solve for the parallel side. So I'm going to rearrange this equation. This part, I don't need to worry about that. And I'm going to, let's see, trying to find FG parallel. Okay, so I'm going to multiply both sides by FG. So FG parallel is equal to FG times the sine of theta. All right, nice and easy. Now what is Fg? Okay, Fg is the force of gravity pulling it downward. We are given the mass. Okay, that's not a problem. We've got this. We know that force is ma. Okay, more specifically, the force of gravity is equal to the mass times the acceleration of gravity, g, 9.8. So I'll just kind of put that in a bubble. It's a little, we need to remember that. So I'm going to rewrite this equation with that in mind. So the force of gravity parallel is equal to Fg, which is going to be mg times the sine of theta. Okay, now it specifically asks for the number, so we're going to plug in these numbers. The mass is 200 kilograms. All right, the g is 9.8 meters per second squared, and sine of theta, which is 15 degrees. And if we put that into our calculator, making sure it's in degrees mode, my FG parallel is 507. We'll stick to 29 for now. Okay, that'll be fine. We're not talking significant figures right now, and that's fine. Okay, so we just found our Fg parallel, the force of gravity parallel to the ramp. That's how much force the block is being pulled down the ramp. We also have to find the FG perpendicular. So to do that, I will basically do the same thing except with cosine. So where should I write this? How about here? So we remember cosine of theta is equal to, so that's ka, so A over H, and our adjacent, if we look at our triangle, the adjacent is FG perpendicular, and the hypotenuse is, once again, the FG, the force of gravity. So if I rearrange that one, again, we don't really worry about that, then that ends up being FG perpendicular is equal to FG times cosine of theta. Okay, we see a pattern here. Knowing what we already know, the mg, FG perpendicular is equal to mg times the cosine of theta. And so that is our mass again, 200 kilograms times 9.8 meters per second squared times the cosine of 15. I wrote theta again, but we could actually write our, we're actually solving for it right now. 15 degrees. And so our FG perpendicular is, when we put that into our calculator in degrees mode, 1,893.21 newtons. I'll put a box around that. There we go. It's barely in the screen. Okay. So now we have our answers to part A. So what I'm going to do, just kind of like put a little thing around there to separate A from the next one. But that's how you do finding parallel and perpendicular components. All right, so now letter B wants us to find the normal force. Okay, the normal force. That's not a problem. Here's why. What we know is this. First of all, if we look at our diagram again, let's pull that down. Okay, the normal force is, again, it's perpendicular to the incline. Okay, it is not directly opposite of the force of gravity in this case, because it's all at an incline. It's not on a flat surface like we're used to. It is, instead, it's on the opposite side of the force of gravity perpendicular, which we just solved for. Okay, now we could jump to conclusions here, but I'm going to walk you through this whole thing so you know why the answer is the answer. Okay, the sum of, now this little symbol here is, it means the sum of all the forces in the perpendicular direction. What do we've got? What do we have? Okay, we have basically the normal force plus, and then if we look at our little diagram, we've got our force of gravity in the perpendicular direction. It's in the opposite direction. The force of normal is sort of pointing up-ish. This one is sort of pointing down-ish. It's gravity, so it feels like it should be pointing down. So this is going to be a negative force of gravity in the perpendicular direction. Okay. We also know that the sum of the forces from up here, I should have written F net. Okay, we know the sum of the forces, the net forces, is going to equal mass times acceleration. Okay, where am I going with this? Well, what is the acceleration of a block that is just sitting there? Right, this is going to be 0. The acceleration is 0, so we know that this whole thing is 0. It's going to be equal to 0. Okay? What that means is, if I rewrite this a little bit more useful, the normal force minus, I'll just, skip straight to that, minus the FG perpendicular is equal to 0. Those have to add up to 0. Okay? In other words, if I take that, the force of normal is equal to the force of gravity perpendicular. Okay, that's the long way of saying what you already knew, but it's important to understand why. So the final answer here, the normal force is equal to whatever we got for the perpendicular force of gravity up above. That was 1893.2. I'll put 1, but I feel like I should round that a little bit better. Okay, so that is our normal force. That's letter B. Okay. Letter C. Should I write it over here? Let's go kind of below. We'll do this. Letter C. How's that look? All right, that's not too bad. Letter C. Let's see what letter C is looking at. It wants to know the force of friction that keeps the block from sliding. Okay, that's cool. We look at our diagram again. And this is why drawing the force diagram really helps right away. The force of friction is static. It keeps the block from sliding. And the way it works is basically, we've got our vectors here. The force of friction is going up and to the right as I drew it. And the gravity, if I were to redraw this, I could redraw this right here. And that is pulling down and to the left. And so those two are going to end up being equal as well. But let's just double check ourselves and make sure. So that's going to be our force of gravity parallel. So if we take a look at that, once again, the sum of all the forces in the parallel direction is equal to, hate when that happens, is equal to the force of friction that's static, the force of static friction, plus, and the reason I'm using it this way is because the static friction is to the right, and usually when we say something to the right, we're going to say it's a positive, and when something's to the left, we're going to say it's a negative, just to be consistent. So, plus the negative of the force of gravity in the parallel direction. Okay, and once again, F equals ma, so the sum of the forces, the net force, is equal to ma. We know that acceleration is 0 because this thing's not moving. So I'm going to just do one of those and just get rid of that, which means it's equal to 0. Looks familiar. We just did this, right? So if we rewrite that in a somewhat more useful way, the force of friction, static friction, is equal to, well, you know, I'm slightly jumping the gun. I don't like to do that. I put the one little sign and then minus, because it's kind of plus negative, the force of gravity parallel is equal to 0. Okay, it's important to understand why we're doing this. So finish this off. The force of static friction is equal to, we subtract that one from both sides, is equal to the force of gravity parallel. Okay, and so what is that equal to? Well, we already know the answer to that. We have figured that out. The force of friction, static friction, if we look at above, right here, literally right above us, is 1,893. And again, significant figures is not a thing we're doing. So I'm just going to round it to something that seems reasonable. And that would be our static friction. We have answered the 3 questions. Okay, now, because I can't just leave it at that, what about that coefficient of friction? What about it? We can now solve for it. Okay, so if I were to just kind of do a bonus question, what is the coefficient of friction? There's 2 ways to do this. First, we're going to start with what is the equation for the coefficient of friction. Well, we're going to say the coefficient of static friction, and we're going to assume this is the maximum. We're going to assume that this block, if it were lifted even another 0.1 degree, would start to slide. This is the maximum that this block, the maximum angle that this block could stand without actually sliding. So we're gonna figure out the maximum here is equal to mu, the static mu, times the normal force. Okay, that's our equation. So not a problem, right? So the mu, the coefficient of friction, if we divide both sides by normal force, will be equal to the force of static friction, the maximum, which we're going to assume that's what we have, divided by the normal force. Okay, so that would be our equation. We could plug in the numbers we already know. We already got the static force is 1,893.21 newtons. And our normal force is Where was that? Oh, I made a big mistake somewhere, didn't I? I sure did, Mr. Chern. All right. If you actually put in the numbers correctly, which I did at some point or another, this becomes something else entirely, which means this will become something else entirely. The thing is to check your calculator every now and then, make sure you're doing this right. So 507.3 newtons. All right, we'll call it that. We said that earlier. Up above here, 507.29. I just looked in the wrong spot. So double check your work now and then. Take this as a warning. I'm going to leave this in the video because I think it's important to double check your work. Okay, so that didn't sound right. So watch out for little red flags popping up like that. So 507.3 newtons divided by, now this is where the 1,893.21 newtons comes in. When we do the math there, the newtons cancel out, and we're going to be just left with a ratio essentially, and it'll be about 0.27. Okay, that would be our coefficient of static friction here. Bonus. Let's say we didn't do any of those calculations previously. Well, if we instead didn't know the answers to those, then if we took the, here, let's just do this, static friction is equal to the force of static friction max divided by the force of normal. Okay, static friction, how did we calculate that? Well, we took mg, if you remember from up above, times the sine of theta. Okay, no numbers yet. The normal force was calculated by saying mg times the cosine of theta. Okay, and if you don't remember, here they are right here. This is how we calculated the parallel, which ended up being the static friction. And over here is how we calculated the perpendicular force, which ended up being the normal force. So we plug that in. Now look what happens here. We've got mg over mg. That's going to cancel out. And so to calculate mu, all we have to do is take the sine of theta over the cosine of theta. And that seems weird, but when we do this, the sine of 15 degrees divided by the cosine of 15 degrees, we put that in the calculator, and what do you get? 0.27. Same exact answer. Let's here. There we go. Same exact answer. So hopefully that's helpful to you dealing with things on objects on an inclined plane. Not too terrible once you get the hang of it. So good luck.